Ze względu na wcześniejszą porę i zmianę sali można było jeszcze 5 minut zaczekać.
Nie, ale speaker się spieszy.
Okay, so we're back with our seminar. Today we have the Transcarpathian seminar on geometry and physics. Today we have the great pleasure to host Alexander Schmeding from Trondheim. In Norway, Alexander is an expert in infinite-dimensional geometry, especially, or in particular, that related to Lie groupoids, groups of bisections, the tangent structures. So we're very hopeful that Alexander gives us a very gentle walk through the realm of those infinite-dimensional beasts. So, Alexander, the floor is yours.
Yeah, thank you very much, and thanks for the invitation. So let's hope that I manage. I mean, the plan for today, as I understand, we have these two roughly 45-minute blocks, and so I think, I mean, there are several heavy lifting components, if you want, to this talk. I mean, on one hand, it's infinite dimension and then higher geometry, and depending on what your background is, you might know one of them, both of them, or none of them. And so, I mean, typically what happens, I'm always saying this, but in case everything is too easy, then you're telling me, and then I speed up. But this usually never happens. But also the converse, in case you have any questions, please ask right away. So I will then try to either give another explanation or give more details. And I would suggest to ask directly via audio, because experience shows that I'm extremely bad in noticing if somebody types something in the chat. It's a pleasure to actually be at the seminar, because as I saw from your webpage, lots of the people who are listed as friends and or regulars are people I either met at conferences but very long time ago, or have read their papers over the years. I mean, I see that Cornelia Wisman is here, and I mean, you cannot go around this business with these infinite dimensional differential geometry without stumbling upon some of her work, I guess, or at least in my case, that's true. But let's go to the first part of the talk, which I would like to call from finite to infinite dimensional, or and let's start maybe a bit weird, in case because in the end I want to go to the bisections of a Lie groupoid, but let's do something which on first glance has apparently nothing to do with all of this. Let's look at the heat equation on a circle. So basically one finite dimensional application of all this theory I want to show you today might be that you want to understand how the heat flow on the unit circle S1, which I've drawn here as a torus, just to show the distribution of heat by color, evolves. And then physicists tell us that there is the heat equation, which reads like this. So we're seeking a time-dependent vector field on the circle, giving us the temperature, starting from some initial distribution and satisfying this equation, time derivative is equal to the second order spatial derivative, where theta is now the spatial variable in this. Okay, and now you might ask, okay, why I thought this was about geometry. Why is he talking now about PDEs? And this will not be a PDE talk, but I want to give this as a motivational example of how a lot of the objects I'm going to talk today about are arising, let's say, in nature, or for lots of people without them even realizing that they want to be talking about something infinite dimensional. The point is, I mean, I'm really bad in doing partial differential equations. I mean, especially when I'm talking to my colleagues who work with these things, they always laugh at me at my attempts to solve these things. But what I can do reasonably well, I can solve ordinary differential equations. And of course, the main annoyance is that this is a partial differential equation, it's not an ordinary differential equation. But here comes sort of the trick. So instead of thinking of the u as a function of two variables, I can basically hide one of the variables. And we are now in the happy place where all of the functions are smooth, right? I mean, in general, we are searching for way rougher solutions, but let's pretend that we are only searching for smooth in space and maybe smooth in time solutions of this equation. And there's this little trick where I'm just saying I refuse to evaluate in the spatial variable, and I just want to write the u, which is a function of two variables, as this u v, a function which is now a curve. So it takes a time variable and takes its values on the smooth functions from S1 into the reals. And basically why I'm giving you this example and why I'm talking about it. So this idea is transporting immediately, or your finite dimensional problem, and transports it to an infinite dimensional equation, where now we are talking about a curve taking values in this space of smooth functions. I mean, this is a vector space. We can add these things. But it's infinite dimensional, yeah. So when you put a topology on it, this is not even a Banach space because we have infinite order of differentiability. So we need some other tools, well, in this case from calculus to treat this. But the nice effect here is, so this is not an infinite dimensional vector space. Sorry, this is an infinite dimensional vector space, but not a Banach space. That's what I wanted to say. And if I look at the operator d, which sends a function to the spatial derivative, this is now a linear operator on these things. Actually, this is also sort of explaining why you cannot model the C infinity functions as a Banach space, because otherwise the d here would have, you would know something about the spectrum of the d, because this is a continuous linear operator on the C infinity functions, and would have a nice spectrum, and you can immediately construct examples which are basically infinitely large in the spectrum of this operator. So if you want that the C infinity functions are a Banach space, definitely the D operator here cannot be continuous linear. Anyway, so what we basically have, so instead of the partial differential equation,
Can I ask something?
Yes, sure.
Isn't the spectrum like integers and it's just
Yes.
Yeah, so what about the spectrum?
So in case, so how was the theorem I was referencing again? So I think if you have this continuous linear operator, in this case, it would be bounded, I guess.
Right.
And that's something you cannot have, because exactly, I mean, let's do it even easier. If it were the C infinity function from the reals to the reals, right? Then you have the exponential to the so e to the nt or something like this, which is
No, but in the reals it's not true. But on S1, I mean, if it's on the line, it's not. But S1, I think it's fine, right?
Let's see. I think you can do the same thing with I would have to check, but I think you can construct a similarly counterexample for this one here. I mean, this all okay. Let's would have actually. This is why okay.
I think like sinus and cosinus, and there's nothing else, I guess, no?
I can check later, but I think there's also in the. I mean, okay, there are also other. Okay, then let me give you the example. I mean, let's not pretend that this is really sort of the reason why I want that this thing is not a Banach space. I mean, actually, what the topology on the C infinity function should be doing is it should measure a function and up to as many derivatives as you want. And then you can think of how the semi-norms look like, which give you that, and that it cannot be, and then you see that this cannot give you a norm, basically because you have infinitely many differentials you potentially want to control, and this cannot be done in a norm. So this may be the better explanation without going to the spectrum of the operator D here. Okay. Okay.
Excuse me, I have a remark that this kind of equation has a simpler solution. Namely, you can perform Fourier transform, and each Fourier mode has its own the same differential equation, and you can solve them explicitly, and then that's the solution. Of course, you need to embed this C infinity into Hilbert space, but
yes.
who cares?
Yeah, no. I'm basically, this is this is sort of like a bit of a phony application, right? I mean, the reason this slide is called the heat equation a la Hamilton is basically, I think, because the examples are going back to Hamilton's famous paper about the Nash-Moser inverse function theorem. And so this is usually not, well, at least not the only reason why you want to be looking at this.
Let me clarify the remark here. So I think the issue is completeness. So of course you could use the subnorm S1 is a complex space, but then C infinity functions in the subnorm, they don't form a complete space. So if you want to complete, you are going to get L2 functions. Right?
Yes.
But you want some kind of complete locally complex vector space, and we can achieve this by using this countable set of semi-norms, right? Then we get a Frachet topology. That's complete in the sense of a uniform structure, but it is not complete in the sense of a Banach space. You don't just have a norm, you have a countable form with semi-norms. And that's what Alexander was trying to say.
That is true, yeah. Thank you. All right. So, I mean, basically, I'm giving you this example to say, even if you're interested in finite, I mean, and nobody's, okay, even if you're interested in finite dimensional problems like the heat equation, you might hit upon infinite dimensional spaces which are beyond the realm of Banach spaces. This is basically why I was bringing this example. Because then, instead of solving this partial differential equation, we have a linear differential equation, but now on an infinite dimensional space. And I mean, there are serious applications where you actually want to do that. I mean, for the heat equation, most probably you don't want to do it because, I mean, for example, you have the Fourier transform or other PDE methods to actually do this. The reason why I still like the example is that it shows that sometimes you can trade difficulties. In this case, the difficulty of solving, okay, an admittedly not so difficult partial differential equation for the solution of a linear differential equation, or an ordinary differential equation in this sense, but you have to do it on an infinite dimensional space. So if you know a lot about infinite dimensional spaces and how to solve differential equations on them, you might get away with doing that and trading sort of your knowledge on infinite dimensional spaces for a solution of the differential equation. That's basically the reason why I want to give you this example. So let's maybe move away from the differential equation now, because this is sort of just meant as a motivation example of how infinite dimensional spaces might arise, even if you want to think about something which is purely finite dimensional. This is basically the reason why I'm bringing this. Okay. However, the question is basically, I was doing a crucial step here. If you're going from the U to the UV, basically the U is, well, let's see, because we're in the nice world where everything is smooth. This is a smooth function of two variables from the interval times S1. We are going to a function on the time interval, but with values in this infinite dimensional space. And I was just claiming, okay, well, so this, since the U is smooth, also this curve UV is smooth as a curve into this infinite dimensional space. And the partial differentials, they basically translate to the differential of the UV, and the right-hand side, so the second order or applying 2 times this d operator to the UV is the same as if I'm doing 2 times partial derivatives of the U with respect to the spatial components, and then I take the V operation of viewing this as a map into the infinite dimensional thing again. So, and well, the question is, well, can one actually justify this? I mean, so far I was just claiming that it works, and generally people tend to believe that this should work out, right? I mean, what other differentiable structure you would have on the space of smooth functions? So a sane thing to assume if you're talking about these spaces of smooth functions is that such a thing should work, because otherwise it's probably not worth to talk about these spaces of smooth functions. But since it's not a Banach space, but as was pointed out earlier, it's a Frachet space. So the question is also, what do we actually even mean by differentiability? right? Because usually differentiability would be, I mean, if you're writing down the differential quotient, you're looking at the total derivative. This is something which is getting written down by using a norm on the vector space. And there are the classical examples where you can see that the classical definition of differentiability only works up to and including two Banach spaces, because you really need a norm. Because the point is that the differential in the classical setting wants to be a continuous, or if you have a C1 differentiable map, you want it to be a continuous map into the linear operators, and the linear operators then also need to be to get some topology so that you can talk about continuity. And what you want there is the operator norm, and there's no replacement for the operator norm beyond Banach spaces. So there are actually also no-go theorems. You cannot nicely topologize the continuous differential, the continuous linear operators between, let's say, Frechet spaces with a topology which lets you get away with such an operation of differentiating. So we need a different notion of differentiability. And there are several choices you can make. And let me just give you an extremely brief.
Let me comment. May I
Hmm?
comment on the so of course the question of the differentiability for locally convex spaces has many variants, but your example could be misleading from this point of view, because you deal with curves.
Mhm.
And this is the particular case of curves, namely curves in every topological vector space. The differential of a curve has an ambiguous meaning. Yeah.
Yes, that is true.
Yeah, because this is the limit of the difference quotient. While of course more advanced maps with many variables or from one space to another, this is completely different question, much more complicated. But curves is a very simple example. So this makes sense for any topological vector space with any problem.
That is true. Yes, thank you very much. So this is a good point. I mean, basically, the motivations I'm trying to take some shortcuts here. Yeah, and I mean, later on when I'm actually showing you some arguments based on the tools I just want to show you, they will mostly be involving curves. And as was just pointed out, this is never a problem. Actually, there's also no ambiguity of how you define it. So for the, I mean, what I will need the notion of smoothness now for is I want to define in a few slides what I mean by an infinite dimensional Lie group, right? And then we will have a group object where I need to make sense of smoothness of the group operations, and there we will have honest maps which are defined on an infinite dimensional manifold. In the following sense, and take values in an infinite dimensional manifold. So this is something where you then need you need to decide for some calculus. I mean, before this comes up later on, today I will only present to you the most elementary case of the results which you can do, let's say, for example, for these bisection groups. The reason is that sorry?
But what means partial derivatives? Of course, on infinite dimensional space, there is no concept of partial derivatives because there is no concept of a basis.
Yeah.
So.
Okay, let me, sorry, let's do, let me write something down. So, okay, what I
There
actually.
are no coordinates in a space.
This is true. I maybe should have written directional derivatives. That would have been better.
What are
Okay.
coordinates in a Banach space?
Yeah, no, you don't need coordinates here. So basically, I mean, if you want, so this is why I have this thing here. What I basically want to define, if I have a function f, so I basically want to define this differential quotient, which is just, if you want, the Gatto derivative. in the
So you mean
Direct-
directional derivatives rather
Yes.
than partial?
Yeah, this is actually an error on the slide. So exactly. So we want the directional derivatives. Okay, these things should exist and then glue back to a continuous map on, okay, let's say our function f is defined on some open subset of a locally convex vector space with values in another locally convex vector space. Then I basically want the df. So all of these directional derivatives, I want them to glue together to, let's say, U is an open subset of E. I basically want this map to be continuous. So first of all these limits should exist. I mean, what I do here is x and v are then basically getting sent to df of x. Sorry, I need to remember my notation here, like this. Okay. And what you see here is basically the difference of what this Bastiani calculus is doing. It's basically avoiding the mentioning of any topologies on the linear operators. I mean, if you have a locally convex space and you have so if this exists and is continuous, we say df. We say f is C1 map, or C1 in the Bastiani sense, I should say. And yes, so the okay, this is basically what I wanted to say there. Yeah, so there's an error on this slide. So it should be directional derivatives. Sorry about that. So there are some other choices actually for the people here who know. I think a lot of you are maybe familiar also with the convenient setting of global analysis. Since we are only doing or mostly doing the easiest version of the results, which will lead us only to manifolds modeled on Frechet spaces. Since this Bastiani calculus is on Frechet spaces equivalent to the convenient calculus, you could also do these things equivalently with convenient ones, or with the convenient calculus where you test against smooth curves. Well, okay.
How you came to locally convex? Because the Bastiani doesn't. Every topological vector space is okay to define the directional derivative. So how this locally convex appear?
You need locally convex to prove the chain rule. That's basically the point. If you want to prove a chain rule for Bastiani C1 maps, let's say, you need local convexity to establish the chain rule. Because otherwise you run into all these pathologies which you usually don't. I mean, in essence, you get the chain rule from a version of the fundamental theorem of calculus, and that is true on locally convex spaces, and on general topological vector space you have these pathologies which we basically avoid by asking locally convex. On a general topological vector space you can have mappings which are injective and their derivative vanishes identically, and locally convex is basically by giving you a version of the fundamental theorem of calculus avoiding this pathology. All right. So, and then basically for an infinite-dimensional manifold, you can use the usual chart definition, where the change of charts are then smooth in this Bastiani sense. And one of the examples, well, basically actually more or less the only example I want to show you today, because they are the most important ones for us, will be the so-called manifolds of mappings, where well, for presentational reasons, I restrict here to K a compact manifold as the source manifold from which the smooth mappings go into another manifold. There is no real reason to do this. I mean, what this nets us is that the topology on these spaces is nice, and that we will get a nice tool for these spaces which is not present if we allow as a source manifold K some non-compact manifold. So for the sake of presentation, I'm cheating here because I'm only showing you the results in the version where we have always a compact source manifold. But all of this can be done, but with a lot of greater technical difficulties for non-compact source manifolds. And so basically, the C infinity functions from one compact manifold to an arbitrary manifold. So the M might be infinite dimensional. So in the above sense, that really doesn't matter. Apart from that, we need some other tool in the construction, which but I don't want to go into the details. So what is fine? Let's say, for example, this works for any finite dimensional manifold and for an infinite dimensional manifold with assumption of some additional structure, which is called a local addition, but I'm not going into local additions today. So the main reason why I stay with compact manifolds is that there is one nice tool which one gets here for these manifolds of mappings, which is in the Bastiani calculus as such only true if you assume that you have a compact source manifold. In the convenient calculus, it's true a little bit more general. And this is the so-called exponential law for smooth mappings. And basically, it states a map G from any manifold, n might be, so the manifold n might also be infinite dimension, it doesn't matter, into this manifolds of mapping is smooth if and only if this associated map, G wedge, so this is now the associated map of two variables, where we take first an n from n, send it to Gn, which is a smooth map eating things from k and spitting out stuff in m, that this is a smooth map. And so this is a theorem in Bastiani calculus. And depending on what kind of calculus you choose on infinite dimension manifolds, this is either a triviality or you need to work for something. And so this exponential law for smooth mappings is something as it's in a certain sense for this other calculus, which I usually don't work with, the convenient calculus, but which will be equivalent, at least in the examples we are looking at today, to the Bastiani calculus. This is their base assumption that it holds. And so in a way, I get around explaining to you how you actually build these manifolds of smooth mappings, because this exponential law can be used to calculate a lot of things for these manifolds of smooth mappings. And the first thing I want to explain to you, how do you use this exponential law to actually find the tangent bundle or the tangent manifold of these C infinity functions?
So may I ask why is it called exponential law in the sense of Cartesian structures? In what sense is this exponential law? It sometimes explains me that you can introduce a Cartesian structure for smooth maps, right? On this category, something like a Cartesian category. That's the idea.
Yeah, that's in principle the idea. It's weaker, of course, than Cartesian closeness, because it only works if the k here is compact. Right? Yeah, so this is what I want to assume. And I mean, there, for example, this old book by Michor from 1980, where he basically tells you that this is the strongest form of an exponential law you can hope for in the Bastiani setting.
Okay, thanks.
So there's basically no chance at Cartesian closedness of let's say smooth, possibly infinite dimensional manifolds with Bastiani.
Okay, thanks.
All right. So, and basically, as an example application, what I can at least motivate. I'm suppressing some details. So, if you want to compute the tangent bundle of the smooth manifold, or let's say we want to compute at least first the tangent spaces at a mapping F. So then, well, depending on what your definition of tangent space is, mine is basically an equivalence class of smooth curves. So there we are again at the smooth curves running through the base point. So f is a smooth function, and we basically want to consider now a curve gamma from some interval containing 0, taking values in the infinite dimension manifold. And this is exactly something we can hit with this exponential law. So I can basically go from the gamma to the gamma wedge. So what this is telling me, we can consider the gamma wedge. This is now a mapping of two variables, and we can basically calculate the partial derivative of this gamma wedge with respect to the time parameter. And for every single point in the manifold K, we then get this differential. And it turns out that we can identify this class of curves, or the derivative class of the curve gamma. We can identify this with a mapping capital F, which goes from the original manifold K, but takes values now in the tangent bundle of the target manifold. And it's based because we are taking the derivative at time t equal to 0. What we see is that since gamma of 0 is equal to f, it's the map capital F sits in the tangent bundle over the graph of this function f where we started from. So in principle, what this allows us to do is basically the tangent space at the small f. Those are smooth mappings from K, which take values in the tangent bundle of M and cover the map we started with. So this gives one a natural identification of the tangent bundle of the smooth functions with the smooth functions from the same source manifold, from K, but with values in the tangent bundle of the target manifold. And you can iterate these things.
Let me mention that this is the approach, very old one, namely, this is the approach used in the variational calculus. And you see in the variational calculus, curve in the space of curves is a homotopy, etc., etc. But you see, so physicists did it and use it for hundreds of years, but they didn't care about the topology on these infinite-dimensional spaces, because to do the corresponding calculations, no topology is really needed. So this topology is just the mathematical idea to put some order into this, to formalize this. But
well, I would object. They did care about the topology under the following circumstances. If they wanted to do pre-quantization, they would like to put the topology on the phase space and, for example, erect a bundle over it, which would pre-quantize the theory. This is how I came across this compact open topology where the compact source was needed. So some physicists, let's be more...
one can put, of course, and consider, but the original idea of variational calculus worked without any topology. Yeah, so this is just to mention that sometimes the topology is not really needed to provide calculations and solve some problems in.
This is true. I mean, insofar the topology is trying to follow and emulate that, right? I mean, this is basically what you would call a sane infinite dimension manifold structure, which enables this calculation, or which is compatible to the physics calculation. You can, if you want, you can see it like that. Yes. Thanks. Okay, and there's one more tool I want to tell you. We will need that later. Which I call the Stacey Roberts lemma, and this is basically there are various iterations of this. So there's the first paper which I wrote together with Amiri, where unfortunately my proof had a flaw, and we are basically remedying this in a new work with Peter Christel, which will appear later this year. So the statement is, if you have a smooth surjective submersion of Banach manifolds, so from Banach manifold M to N, then the push forward map from the C infinity functions from another manifold X doesn't need to be compact. So I'm actually breaking a little bit my rule that I'm only showing you these things with compact source. But okay, what can one do? One could assume that the X is compact, but it doesn't matter for this result. So this is a smooth map, and it turns out to be also a submersion. And submersions make sense here because, well, it depends on what your definition of a submersion is, but the good definition, at least, which works on arbitrary infinite dimension manifolds, is one where in charts you conjugate this to, or you find submersion charts which conjugate the map, which should be a submersion, to the projection onto a complemented vector subspace. So this is a definition.
Here is another problem, yeah, because in general, there is nothing like complementary vector subspace to a vector subspace.
Yep.
Even in the Banach case.
Yes. So all I want to say, I mean, we will use this later at some point, because what this tool gives you in hand is basically if you want to carve out submanifolds in the C infinity functions, you can use the Stacey-Roberts lemma and take, for example, the pre-image under the push forward of the submersion, which will then, by the general statement that pre-images of singletons under a submersion are submanifolds, will give you a submanifold. Right, so this definition of what the submersion is here, and as was pointed out, it's a real condition to have a complemented vector subspace. I mean, already in the Banach setting, but yeah. So this is exactly built in a way that the general statement that the pre-image of a singleton is a submanifold remains true. Okay, so but let me just swap because to the topic at hand. So infinite dimensional Lie groups. Question is, what is a Lie group? Well, okay, if you ask me, a Lie group, well, not just me, but one possible definition is that a Lie group is a group together with a manifold structure, turning the group operations into smooth maps. And now, since we have Bastiani calculus or some notion of differentiability, we can just copy this over to the infinite dimensional setting. So we know what an infinite dimensional manifold is, what smooth maps between infinite dimensional manifolds are, and then I just say an infinite dimensional Lie group is a Lie group. Is a group which is potentially infinite dimensional manifold, such that the group operations are smooth. So this is, I think, what Karl Hermann Neb in his survey calls locally convex Lie group. I just say infinite dimensional Lie group for this one. Yes. And there are a few new phenomena in infinite dimensional Lie theory. So you might know that that every finite dimensional Lie algebra is the Lie algebra of a Lie group. This is not true in infinite dimensions, and the Lie group exponential is bad. I mean, since Professor Grabowski is also regular in the seminar, I think the strongest result in this direction of a bad Lie group exponential is due to him. Which shows that the diffeomorphism group of the unit circle is in a very strong way not locally exponential, in the sense that the Lie group exponential does not give you coordinates around the identity element.
Can you give some general idea about what kind of infinite-dimensional Lie algebras exponentiate to this notion of infinite-dimensional Lie group?
Unfortunately, no, because the counterexamples, I mean, they are classical. I think the first one is due to, I'm not entirely sure whether it's either Van Est or Kortenhagen or both of them. And I think their counterexamples are already from the Hilbert of Hilbert type or of Banach space type. So as an underlying thing. So it really is sort of, as soon as you step outside into infinite dimensions, there's a topological obstruction appearing, which might prevent you from integrating Lie algebras to Lie groups.
And the topological abstraction is known explicitly. I mean, there's a way to compute it.
Partially, yes. So the Van Est-Kortenhagen argument is basically, I think it's. We'll come back in the very end to it, but there's basically, I think it's a higher homology group which is non-zero, which in a certain construction. I mean, if you look at the Van Est paper, he's basically describing a general thing of how you can integrate a Lie algebra. I mean, this is, for example, can be found in the book by Duistermaat and Kolk, and there is, I think, an H2 in a certain cohomology group, if I'm not mistaken. If that's non-zero, then at least sort of this integral construction will show that that it doesn't that an integration doesn't exist. And this is exactly how I think Van Est was it or Kortenhagen. I can never remember who of these two things are constructing their counterexamples.
So I guess this is some kind of continuous version of Chevalier cohomology or something.
Yes.
Like that. Thank you.
Okay, and here is here are some examples. So if you have a compact manifold GLE group, then you can take the so-called current group, or I mean, the special case would be if K is the circle, you get loop groups. So the smooth functions from, okay, depending on what you call a loop group, I take smooth functions. Some people take continuous functions. But in this case, I mean, since I'm always talking about smooth functions here, let's talk about this. So with the pointwise operations, turn this thing into a Lie group. And this is a so-called current group. They occur, I mean, especially the loop groups in physics, I guess. Right, but let's go to the other example. So the other poster boy for an infinite dimensional Lie group, which you meet always, is the diffeomorphism group. So it turns out that the diffeomorphism, the smooth diffeomorphism of a compact manifold, again, we are doing everything compact here, is an open subset of the smooth functions from K to K. And this structure makes the composition smooth. And so as per our earlier calculations, and I think, I mean, I was basically asked beforehand that I should give a little bit of an impression of why the Lie algebra, let's say, of the bisection group is at it, or what this has to do with the Lie algebroid, which we'll see later. And the first indication I want to give you here is basically to tell you a little bit about the details of what the calculations do for the Lie algebra of the diffeomorphism group. As we have seen, since the diffeomorphism group sits as an open subset in the C infinity functions, we may identify the tangent space at the identity as a proxy for the Lie algebra as smooth functions which sit over the identity, or in other words, those are vector fields of the compact manifold K. So as a vector space, we have the vector fields. And how do we get the Lie bracket? And basically, well, the usual construction, how do we extend a vector field to a right invariant vector field now on the diffeomorphism group? It turns out that the way to extend it is basically just by composition. So X is a vector field on K. I can compose this with eta, which is a diffeomorphism of K, and I get something which sits in the tangent space over eta. And this thing is a right invariant vector field. And now we can use the canonical action of the diffeomorphisms on the base manifold. So what you take a diffeomorphism, just evaluate it in K. And a calculation then shows that the Lie bracket of, well, you take the right invariant vector field times, okay, you need the vector field of the zero vector field on K. And you do the same thing with, oh, that should be a capital Y. So this Lie bracket is alpha related by this action to the ordinary Lie bracket of X and Y. And the upshot of this is, because we were using right invariant vector fields, and here it's really important to use right invariant vector fields because the formula for left invariant vector fields is different and more complicated. What you see is that you get, by the relatedness notion, you get as a Lie bracket on the Lie algebra of the diffeomorphism group, you get the usual Lie bracket of the vector fields X and Y up to a minus sign. So this is because we are using right invariant vector fields, not left invariant vector fields. So we need to put the minus sign on top of that.
So I was always thinking right or left invariant at this stage is a kind of convention, but you say left invariant is so much more complicated, except for the sign.
Yes.
Why?
If you because you see what is happening here. So the X composed with eta. This is basically, I mean, how do you construct right invariant vector fields? You take the tangent map of the right multiplication, right? And on the diffeomorphism group, the tangent map of the right multiplication turns out to be just composition with the thing you right multiplied with. If you do this with a tangent map of the left multiplication, you see that you basically need the derivative of eta. For the left multiplication. So you get from the left, you basically get something you apply to the X from the left, the tangent map of eta, and then you have a harder time to interpret this as a tangent vector which sits at the eta. So here it makes actually a computational difference. I mean, in the end, it gives you the same thing, but this this has something to do with the fact that there's a nice formula for the derivative of the right multiplication on this Lie group, but not for the left multiplication. I mean, it's not terrible, but it involves the tangent map of the eta. That is sort of a problem in the calculation here.
Thank you.
I think the fundamental property of the diffeomorphism group in this case is the fact that vector fields generate one parameter subgroups. So you can, to define the bracket of vector fields, you can use the Trotter formula. Yeah, so
Yes.
there you take commutator of one parameter groups and you calculate the derivative, yeah, which is second derivative in this case. But the fundamental is that vector fields induce one parameter subgroups, which is not true for a general one parameter infinite-dimensional Lie group, yeah, which causes them many problems.
Yes, let me make a snarky remark from the mathematician here. The Trotter product formula is one thing which also works out in this case here, but from the outset, without further information on the infinite-dimensional Lie group, you cannot assume that the Trotter product formula is true. I mean, here it works again, and physicists are right that you can exactly compute with the Trotter product formula, but from the perspective of this infinite-dimensional Lie theory, it would be that you need to prove something for these things, because the validity of the Trotter product formula is always true in finite dimensions, and on Banach, yes, on Banach Lie groups, but beyond Banach Lie groups, you can produce counterexamples. I mean, they are a bit artificial, where the Trotter product formula fails. Okay, this was sort of the snarky remark of the mathematician. Yeah, so actually you need sort of this notion of regularity, but let's hop over this thing. Let's maybe go. Let's maybe just mention one thing. So because I'm running a bit short of time, and these things in the intermediate were not that important, at least for what's coming next. But one thing I wanted to mention. So if you have a compact manifold, you can, of course, compute the diffeomorphism group. And then the question might arise, so what does the diffeomorphism group know about the underlying manifold from which it sprang? And it turns out this is what I mean, there are actually a lot more names attached to it, but I think in this version it's a theorem which appears both in papers, or I mean, this appears in various versions, and one paper is by Tarkins and the other one by Filip Kiewicz. I hope I'm pronouncing this correctly. I'm sorry, I don't speak Polish. So basically,
theorem is true for Lie algebras of vector fields.
Yes, this is actually where it's coming from. Yeah. And however, it shows if you have a group isomorphism of the abstract groups, so nothing about Lie group structures here, just about the abstract groups of diffeomorphisms, then also the two underlying manifolds are diffeomorphic, and actually the group isomorphism is then induced by the diffeomorphism the following way, that you basically, if you have the diffeomorphism gamma, let's say from M to M, then phi of gamma is then basically just conjugating with the with psi and psi inverse, right? So in a certain sense, the diffeomorphism group remembers the underlying manifold from whence it came.
Well, in this result, M and N have to be finite-dimensional manifolds.
Yes, this is for finite-dimensional manifolds. I mean, the diffeomorphism group I can actually only in a satisfying way write down, because there are some problems with the function space topologies. If your source manifold for the C infinity functions is not finite, or in other words, if it's not locally compact, that is basically a problem for the function space topologies on these.
I see. Thank you.
Okay, and So if we want, we could read this as an algebraic reconstruction theorem. Yeah. So basically, this infinite dimensional group carries enough information about the manifold from which it was constructed to recognize it. Yeah. So this is something I would like to note as a reconstruction type result, which will be maybe of interest to the second part. Speaking of the second part, this would be the second part, linking infinite dimensional Lie groups and Lie groupoids, where we are actually going to what I was asked to do, namely to say something about the bisection group. But since I've been talking for 45 minutes at least, or no, not only me, but also with the questions, I think we should take a break now, right? So I would take this in for the second part.
Okay, so I propose that we make 10 minutes break and meet again at 3 Warsaw time.
Mhm. I'll be right back. think you're still muted.
Okay, so it's now 3 p.m. Warsaw time. We can resume.
Okay, good. So the next piece is sort of linking the infinite dimensional Lie groups with some Lie groupoids. And let me maybe, well, I'm not entirely sure what your background on Lie groupoids, or I mean on the oid part of the series, I mean, which is a sort of higher order thing. And I mean, in case, well, I guess for a lot of you, this might be not new, but let's do a very brief refresher. So if we have a Lie groupoid over M, basically we have two manifolds. One is called one I will usually call M, and M is sort of thought of as a manifold of objects, and the G, the other manifold, this will be thought of as a space of arrows, basically things which allow us to go from one object to the other. And now, of course, all the pictures I draw are usually like these finite graphs, so that we can draw something. But the idea with the Lie groupoid, at least on this level, is so group has one identity. A Lie groupoid, or a groupoid in general, has potentially infinitely many identities. And so the elements in G are basically arrows, and we must have so every arrow must start and end at something. So we have two mappings, which basically are the things which one symbolizes here with this double arrow. So we have a source and a target arrow. They for a Lie groupoid, I want them to be smooth submersions, because I want the I want a multiplication defined on a fiber product of G with itself over the two submersions. And the idea is here, I mean, pictorially, I want to multiply or to compose two arrows if the first arrow ends where the second arrow starts, right? So this is pictorially is this what the multiplication should be? So I have only a partial multiplication, so we can actually just compose things if well, they fit together. And in a group, since we only have one object and we think of the group elements as transformations on the object, we can always compose them. Then there is a unit map which associates to every element in M a unit, which is the arrow which doesn't move, and all of the arrows need to be invertible. That's sort of the other thing. What we need to have. So all of these mappings are smooth, and for the source and the target, we want them to be submersions. This is not the minimal way of, or the minimal thing to ask of as axioms for a Lie groupoid, but yeah. So I mean, I'm not looking for minimal here. And then, as before, since we know what submersions are, we can also have that G and M are infinite dimensional manifolds if we want. As long as we can make sense of smoothness and submersions, everything is fine here. And let me give you some examples, which might, well, the first and obvious example, every Lie group is a Lie groupoid. When I just put the group over the 1-point manifold. Okay, I mean, this is basically like superfluous technicality, but in principle, it tells you again that the higher or the Lie groupoid inherits at least all of the problems you get from Lie group theory, or if there are problems or things which are interesting. So Lie groupoids will at least have them, and most probably some other technicalities which you need to take care of. But why does one want to introduce Lie groupoids? Well, one thing you could be interested in is, well, let's do some stupid examples first. So first of all, the pair groupoid. If I have a manifold M, then I can construct the pair groupoid, which just consists of pairs. And I mean, the arrow space is just the Cartesian product of M with itself. And then I have the two projections onto the components as being the source and the target map. Multiplication, concatenation. Actions of Lie groups on a manifold can be encoded as an action groupoid. And where the multiplication is basically given by group multiplication, so that it fits together. An inversion is given by the inversion of the group elements, whereas the other, I mean, basically the elements in the arrow space look like a group element and a point in the manifold where it should start. Then, okay, I don't want to talk too much about principal bundles, but for principal bundles, you can construct the so-called gauge groupoid. This is most probably the thing which is more of interest to physics. Yeah, so here's the construction. Basically, I don't want to talk too much about gauge groupoids and how you construct them, but we will meet them later because there is one infinite dimensional group I can associate to all of these groupoids, and this is the so-called bisection group, and especially for the gauge groupoid, it will be something which is also physically relevant again. And then another example, you can have frame groupoids of a rank K vector bundle. So where basically the arrows are linear isomorphisms between the fibers of the vector bundle. And yeah, well, basically the source map is telling you where the fiber is sitting, where the point is you're starting at, and the target then where you're ending up, and the multiplication is composition. These things. So those are 4 examples of how you can get Lie groupoids. There is actually a whole class, and I need to say this upfront because I will not discuss this class here because of what's going to follow. So those are 4 examples of why you might be interested in Lie groupoids, because a lot of differential geometry can be encoded in that. And there's a very large class which I tend to ignore in my own work, which people tend to criticize a lot. And this is if you have a foliation on a manifold. This gives rise to the foliation groupoids. And typically, all I'm going to tell you now in the next half an hour or something will not work, at least not as I presented for the foliation groupoids. The reason for this is basically my methods work with differentiability and derivatives, and the foliation groupoids typically tend to be non-Hausdorff groupoids. The ones which I wrote down here are all groupoids where the manifolds are Hausdorff groupoids. If you're into foliation theory, you usually only require that the manifold M is Hausdorff, whereas the arrow manifold might be non-Hausdorff. And if you're interested in the bisection group and why it's an infinite-dimensional Lie group for a non-Hausdorff Lie groupoid, namely one where the G is allowed to be non-Hausdorff, then you need to read Thomas Rybicki's paper, because I, for technical reasons, always need to assume that I work with Hausdorff spaces. So I cannot, or these things I'm presenting to you, as long as they are from my papers, and there's nothing which, for example, Thomas and other people have written for non-Hausdorff groupoids, my results only hold for Hausdorff groupoids. That's sort of a restriction which bites, especially when you're interested in foliation groupoids. If you're not interested in foliation groupoids, typically the groupoids you're interested in are Hausdorff, so it's not an issue. But if you want to do foliation theory with Lie groupoids, then you typically encounter non-Hausdorff manifolds, and that's something I cannot do. Yeah, so all I'm going to say here is from now on, basically, I'm assuming that all of my manifolds and all of my groupoids are Hausdorff groupoids, in the sense that both G and M are Hausdorff. Was there a comment?
But your results also hold true I mean, the main result holds also true for non-Hausdorff Lie groupoids?
Yeah, that is something Thomas Rybicki was doing. The main issue, so I tried, I mean, I discussed this with him at some point. What is not entirely clear to me, I mean, what I want to be doing is, sorry, I want to go, okay, let me just skip the Lie algebroid. And let's go to something. So basically, we want to discuss this by the bisection group. So those are all smooth maps from M to G, which behave nicely with respect to the structural maps. So if I compose them with the source map, I get the identity, and with the target map, I get the diffeomorphism. They form a group, and they have a natural composition of arrows, gives you the product, which I'm not going to write down. And basically, if you identify these bisection groups for the examples I had, you get, for example, back the diffeomorphism group and so forth and so forth. So why am I telling you this now? to your question, because what my results always do, if your groupoid is Hausdorff, then I can build a Lie group structure on these bisections. And what Tomasz Rybicki's paper is doing from, I think, the beginning of the 2000s, if I'm not mistaken, he does a similar thing in the convenience setting, I believe, for a non-Hausdorff groupoid. And basically, I was reading this paper, and what I don't quite understand is what the construction he does says. If you want, I mean, for me, the bisections are always elements which are sitting inside of the space of smooth functions from the space from the manifold of objects with values in the manifold of arrows. If the manifold of arrows is nice, i.e. Hausdorff, I can make sense of, let's say, the compact open C infinity topology, since we are in the happy place where the manifold M is always assumed to be compact. So the correct topology on the C infinity function is a compact open C infinity topology. What Tomasz is basically doing, he is using a result from he's using a result from yes, from I think from something like topological group theory. And his proof is for the manifold structure or of the bisection group is interesting, because what it does, it says the M here is embedded in G with help of the unit map. For the M, also in the foliation business, you assume that it's Hausdorff, and then from topological group theory, there is a theorem which asserts that there will be a neighborhood of this embedded Hausdorff space M embedded in G, and this neighborhood will also be Hausdorff. And then what Tomasz' proof is basically doing, he throws away the rest of G and works only with stuff which lies in this Hausdorff thing. And my approach
May I
is
ask a question?
Yep.
May I ask a question?
Yeah, sure.
Does it make any difference when you assume that both compositions, also S composed with sigma, is a diffeomorphism?
No, this is,
In
I
this
mean,
sense, you should view bisection as a submanifold in the groupoid, such that the projections are diffeomorphic. Yeah.
yes. This is
Okay,
sort of yeah.
I
Thanks
wasn't
for the
sure whether this
no. Thanks for the question. This is an excellent question, because I'm tending to prefer this definition, which is
because there is
one-sided.
rather quick treatment of source and target.
Yes. So and this is asymmetric in S and T. What I have here, you can also switch them around or have this as both being going to the diffeomorphism. For me, either way is fine. So this is actually, for proof reasons later, is it preferable to use one of them, which is not saying both of them go into the diff of M. But this has purely technical reasons. For later, you don't change the space of things. Coming back to this Hausdorff discussion, I'm always first building a manifold structure on the C infinity functions from M with values in G, and then I carve out the bisections as a sub-object inside of the C infinity functions. And for this reason, I have a certain problem if this thing here is also becoming is also getting to be a non-Hausdorff manifold. So I don't entirely understand how the construction really, I mean, Tomasz is doing in his paper, really has to be related to what I am doing. Okay, I'm not claiming to prove anything for non-Hausdorff groupoids, so I'm really not doing that. Yeah, so and his construction, as far as I can tell, should work for non-Hausdorff manifolds by the virtue of that that he's basically going into a neighborhood which still has the Hausdorff property. But I mean, even after reading the paper and thinking about it for some time, I don't really understand how the two constructions are. I mean, if I would just try to copy what I do for the Hausdorff groupoids to the non-Hausdorff setting, I don't understand whether this would give me exactly the same thing Tomasz is already doing there, or whether this would be something different. I simply don't know. So yeah. Okay. Yeah.
In the
so-
last example, can you explain what you mean by semi-linear automorphisms?
Yes,
Or
they're
maybe
coming a little bit later.
Okay.
So semi-linear automorphisms are the ones. Okay, wait a second. Let me maybe switch to the pet, so we can. I don't want to jump now over to all of these. No.
Okay, if you explain later, then you
Yep.
don't have.
I mean,
Thanks.
basically, those are automorphisms of the vector bundle E, such that whenever I apply this to sections of E, they satisfy a Leibniz type rule with respect to multiplication with smooth functions.
Mhm.
And this Leibniz type rule is given by composition of the smooth function with a diffeomorphism of the on the base of the vector bundle E.
Mhm.
Yeah.
Thank you.
So this will make much more sense later, because we are meeting these. Okay, depending on how fast I talk now, we are meeting these semilinear automorphisms later at some point. So those are the bisections we have here. Let me go one slide back, and maybe this is okay. Depending on your background, this might be sort of a little bit of what you already know, and maybe maybe you're just saying that that it won't be necessary. But in case you are not very familiar with Lie groupoids, I mean, Lie groups have an infinitesimal version by going to their Lie algebra. For Lie groupoids, there is a similar thing, which is basically an oid version of the Lie algebra. It's a Lie algebroid, and this is a vector bundle over manifold. It comes with a vector bundle morphism, the anchor, from the vector bundle into the tangent bundle, such that the anchor satisfies a nice compatibility relation with respect to and there's also a Lie bracket on the sections of the vector bundle, such that the Lie bracket and the anchor satisfy this nice relation you see here. And there is a standard construction which expands the Lie functor from Lie groups to Lie algebras to a functor which makes sense on Lie groupoids, let's say over a fixed manifold M, to Lie algebroids over fixed manifold M. There's a reason why I want to fix the manifold, we will see later. And it's basically done as follows. So first of all, we need a vector bundle over the manifold M. We take, here's an alpha, which I didn't replace with an S. So this should be, so this should actually be TSG. So what you're doing, you're taking an arrow, you compute and you basically compute the source fiber. And then you're taking the tangent spaces of the source fibers for all of the arrows. This makes sense because the S is a submersion. So we're pressing this down, we get something in, we get an object, and we can then basically take all the arrows which start at this object. This is the source fiber, and since S is a submersion, we get a submanifold, and we can compute the tangent space of the submanifold, and we take the union of those. This gives us something like a fibered subbundle of the tangent bundle of G. But we don't want a vector bundle over G, we want a vector bundle over the objects, over M. So we have to pull that back using the object inclusion map. So this is an embedding, and then we are just pulling this thing back, and this gives us some sort of vector bundle over the objects. And then the anchor turns out to be the composition. We're inserting this guy here by composing with the inclusion map into TG, and then we are taking the tangent of the target map. And for the bracket, there is a construction using. This reeks a little bit of the construction you see for Lie groups, where you have in this case also right invariant vector fields. So so you take a section of this bundle, and then you use the partial multiplication. I mean, this is only defined whenever you can actually compose the two arrows H and G in the space of or in the manifold of arrows, and you basically say. We want then to take the value of y, and we want to use the tangent map of the right multiplication to move this to some other point. And if you do all the details and so on, I mean, this is classical, let's say, for example, in the book by Mackenzie on Lie groupoids and Lie algebroids. So this is all of this makes sense. I don't have time to convince you and to do the calculations, but there is basically a way of constructing a Lie algebroid for any given Lie groupoid. And the important thing to remember, because this will be important when we're talking about the bisection group, we get the Lie algebroid will be the vector bundle which is formed in this way. We're taking tangents to source fibers, and then we are pulling these tangents to source fibers back to the unit which sits inside of the source fiber. Okay.
But there is another approach where this is not tangent to the source fibers, but this is just the normal bundle to the submanifold of units M.
Yes. Yes.
Then again, there is no distinction between source and tangent. This is unified in this sense. Of course, they are isomorphic, but.
Yep. So I'm giving you the versions which fit to my definitions. That's basically because I prefer to think about these things. But thank you very much. I know this is correct. There's a symmetric way of doing this, and so those are the bisections. And how do they become a Lie group? Well, first of all. So, I mean, since we are now using my asymmetric definition, we see that the bisections are all the smooth maps from the objects into the units, such that if I push forward with the source map, I get the identity, and if I push forward with the target map, I get a diffeomorphism. So, well, we believe for a short time that the push forward is smooth. So this is why I was showing you this Stacey-Roberts lemma. I mean, the push forward is always smooth for arbitrary maps, but the Stacey-Roberts lemma was stating this for a submersion. So T and S are submersions. So since the push forward is smooth and the diffeomorphism group is open in the smooth functions from M to M, I can basically take the pre-image of the diffeomorphism group under this target map, or the push forward of the target map. And this is an open set omega open in the C infinity functions from M to G. Okay, and now we apply the Stacey-Roberts lemma, which says that since S is a submersion, I mean,
So
S
is normal G now a group, or it's still a groupoid? Because
this is just a manifold. So it's arrow. The normal G here is just the arrow manifold of the Lie groupoid G.
But is this in the first line already? You write curly G is equal to, and then upright G. Is it printed, yes. Right? It's a typo, yeah?
No, why?
Okay, but this is not a normal group. It's still supposed to be the manifold of the total space of the groupoid. I mean, the arrow.
Yes. This G here is not a group. I'm just I like to call my arrow spaces also G. So okay, sorry. Whenever I'm talking about Lie groupoids, the G doesn't mean that. I mean, the normal G here does not mean that that it's supposed to be a Lie group or anything. It's just the arrow manifold. So, but yeah, that's a good question. So this G does not is not supposed to mean that it has any group structure or something like this. Yes, it's just a manifold, and yeah. Okay. Well. So basically, because we have the Stacey-Roberts lemma, so this S, the push forward with S is also a submersion of the infinite dimension manifolds. And if I restrict the submersion to an open subset, then it is still a submersion. And now we see that basically the bisection group is this the inverse image of the identity under this submersion. I mean, again, if you prefer to think of this as those are smooth mappings such that both the T star and the S star map it into diff, then we get the same thing. I mean, the argument would be the same, where instead of the singleton, the identity, I would have to write here diff M again, and by virtue of diff M being open, we would also get this in the symmetric case to just go there. Yeah, and then what I'm hiding again is here, then of course you need also to prove that the group operations, which I also haven't shown you for this bisection group, are smooth with respect to the structure. But it turns out that you get this from usual function space arguments by looking at how these mappings are. You can make sense of these mappings as mappings which make sense on the larger space, C infinity from M to G. There they don't, they are not giving you a group structure. But it turns out that with usual function space arguments, you can basically dissect these group operations into something which turns out to be smooth. So the bisections form a Lie group with respect to the submanifold structure. And this is exactly what I was referring to when talking about Tomasz Rewicki's arguments. He's not doing what I'm doing. I mean, here what you see here, I depend basically on carving out the bisection group as a sub-manifold or sub-object living inside of the C infinity functions, right? And this is something he doesn't do. And thus he gets away with non-Hausdorff things.
But,
Okay.
but it seems not every Lie groupoid admits global bisection.
Yes.
Well, identity is the bisection. The identity is a bisection.
No, well, but
Yeah, you're right. This will come up in a few slides. The bisection group might not be large enough for what you want to be doing with it.
so locally probably yes, but
Yes, local bisections. So what you can prove, they're always local bisections through every arrow. In general, okay, let's maybe give this to just give you a short impression of because I need to do it anyway in a short while. Let me give you one example of a thing which doesn't have enough bisections. So we were talking. So let's say I have a manifold M, then we have the pair groupoid. And this is basically the groupoid, which looks like this. So we have M times M, the Cartesian product, the space of arrows. The source map is the projection onto the first component. The target map is the projection onto the second component. And so how does a bisection look like? So the sigma, I can of course write now sigma 1, sigma 2. Since I want the projection onto the first, so this here is S, and this one is T. Right, and projection onto the first of the sigma, this is the identity on M, whereas the projection onto the second composed with the sigma is just assumed to be a diffeomorphism of M. So I see that the sigma necessarily looks like this, so it's the identity and then whatever the sigma 2 is. And if you work out the group structure, again, I haven't shown you the group structure, but basically what you see, the map which sends the sigma to the sigma 2 in diff M, this turns out to be a group isomorphism. So you can really recover, and this is the isomorphism which turns, so bis of the pair groupoid, this is the isomorphism, so this is let's call this phi. So this phi is the isomorphism, making it isomorphic to the diffeomorphism group. So, okay. And why am I telling you this? So let's assume we have M, and we have that M is can be dissected into two manifolds. So this is a manifold, and this is a manifold. Let's put a dot here for they are disjoint and they are non-isomorphic. Yeah? And if they are non-isomorphic, basically what so I can put an N from N and an L from L, and I get an arrow which points from N to L. And so this cannot be contained in the image of any bisection, because otherwise, this bisection, okay, sorry, this is a bit, otherwise this bisection would need to have the following property. If I take the sigma 2 associated to this bisection, it would take the N to L, but this is a diffeomorphism of the manifold. And okay, let's assume, for example, these two pieces are connected. Then it would have to be a then the sigma would have to be a diffeomorphism which exchanges the two connected parts n and l. So whenever I have whenever I construct the M from non-diffeomorphic pieces, I cannot get a bisection which goes through elements from these two non-diffeomorphic pieces. And then you see that not all arrows admit a global bisection going through this. So this is a problem. I mean, the reason why or not only I, but many people look at global bisections is because you can actually get a group, right? If you do local bisections, you get something which is a pseudo group. And I think you can do leap pseudo groups, but at least then everything gets extremely messy because pseudo groups are, let's say, painful. Yeah. So, but this is a very good observation that we might have too few bisections to do everything we want to be doing. Let's first go to the Lie algebra. So if we compute the Lie algebra of this bisection group, well, it's a tangent space at the identity element. And or in other words, we can also say, since basically this group arises as a pre-image of the identity under this submersion S star, we can say this is the kernel of the tangent map at the identity element of the S star. And then it turns out that there's a canonical identification with the pullback or with the sections with values in the pullback bundle of this bundle TSG. Or in other words, this the Lie algebra of the bisections can be, there's a canonical identification identifying this Lie algebra with the sections into the Lie algebroid. Yeah, so this is, I mean, this is now most probably way too fast, but this is sort of the fastest way of seeing that the Lie algebra of the bisection group has something to do with the sections into the Lie algebroid. Yeah, so this is as a space you get basically this argument here, which identifies it as a locally convex space, if you want.
I'm a bit confused. Didn't you just tell that the bisections, the global ones of some curly G, is not a group? I'm a bit confused.
No, the bisections of the global bisections of a curly G, they form a group. The local bisections, so where you basically only ask, I mean, here these things are global because I want them to be defined on all of M, right? And the local bisections say they are smooth maps on some open subset of U going into this G, which satisfy, well, then a version of these two things. They need to be local diffeomorphisms and so forth. And the composition of them, I mean, the product also needs to be locally defined. I mean, this is why you don't get a group, but only something which is a pseudo group.
Yeah, okay. Then, and in the case you just explained with this L and N, is there something special happening with this in this context?
You mean when you go to local bisections, or
No, here you write global bisections. I use now example that with L.
Yeah, so the example with the N and L, this is an example of a Lie groupoid, and then also of where when you compute the pair groupoid, which we will see this on one of the next slides, which I would say has not enough bisections, in the sense that there's not a bisection through every arrow.
But you get this result.
Sorry, say again?
But you still get this result, the last line.
Yes, yeah, that's not a problem. So this is not related to having enough bisections or whatsoever. You can always do this calculation. You always get this as a vector space, as the Lie algebra. No? And I mean, okay, you also want, of course, the bracket. And so there's a canonical action now of the bisection group on the arrows, which is given by this. So I mean, basically what the bisection sigma is doing, if I give it a unit, namely here then it gives me an arrow which starts at this unit. So in other words, I take an arrow G and I compute with the help of the bisections a new arrow which starts at the place where the G ends, and then I glue them. I multiply them together, having again this picture of that multiplication in the Lie groupoid means composition of arrows, right? So this is the canonical Lie group action of
Sorry,
the bisections
Alexander,
on there.
could you name some classes of Lie groupoids for which there are sufficiently many global sections, so global bisections through every arrow, basically?
Yeah, this is nice. Okay, wait a second.
Source connected ones, certainly.
Exactly.
But,
Source connected is sufficient. So this is basically the sufficient. If you have a source connected, meaning that the source fibers are connected, this is a sufficient condition. I think this is the condition This is, I think, the only condition I know which guarantees upfront that that you have enough bisections. I mean, the thing which I just constructed with a pair groupoid is a bit on the pathological side, right? Because I was just constructing something which is on purpose not source connected. Yeah.
This picture is unclear. So how G is related to the groupoid? So because
is the arrow
yeah.
man.
So it's the non-calligraphic G is always the arrow manifold of the calligraphic G.
Okay.
This is so I'm basically okay, and then just looking a little bit at the time here, what you can do is basically so this was why I was showing you this trick with the diffeomorphism group. Basically, the proof of how you get the bracket on the Lie algebra of the diffeomorphism group is on the Lie algebra of the bisection group is exactly the same idea of how you get the bracket on the Lie algebra of the diffeomorphism group. You use this canonical group action to show that right invariant vector fields on the bisection group are related via the action, or I mean the bracket of them is related to the action to the bracket of the Lie algebroid. Remember, the Lie algebroid was specifying a Lie bracket on the sections of this vector bundle LG, which we briefly saw earlier. So, and when you do this calculation, when you look at the relatedness condition, it spits exactly out this Lie bracket, which you have, which is specified by the Lie algebroid. So, in a sense, this is very pleasing because it basically tells you that the Lie algebroid, the sections of the Lie algebroid are giving you the Lie algebra of the bisection group. I mean, not only as a vector space, but also the Lie bracket. So, and for basically what, so maybe in the next 5 minutes, what I'm going to tell you, the reason why all of this works is basically because of this connection of that the Lie algebra of the bisection group is the section algebra of the Lie algebroid. This is in the background driving all of these results I'm going to talk about. Because this is giving you a lot of extra structure, so that you're not you never get as Lie algebras of bisection groups arbitrary Lie algebras. They always arise as section algebras of the Lie algebroid, and this is an extra structure which well, in disguise, a lot of the constructions are leveraging if you're working with these things.
But this cannot be true in general because the right-hand side has always non-trivial meaning and the left-hand side could be trivial. No, if you have no bisection except for identity, so
I mean, okay. I mean, basically, so I mean, basically, it's telling you that that as long as the right, I mean, as long as I mean, when we're constructing this vector bundle and it has sections, then you get a Lie algebra which is richer than just being trivial, right? So this is I mean, in a certain sense, it always tells you that there will at least be some bisections, which are, I mean, it depends a little bit on what your groupoid is, but
To on mi tyle, że to tylko otoczenie identyczności będziesz miał te bisections.
Yeah, Lie algebroid is a very well-defined object. This is a vector bundle, so has plenty of sections, etc. Yeah. So in a best known case, there's a vector fields on a manifold. Yeah, for the pair groupoid. But bisections, if I don't know anything about the Lie groupoid, I don't know what.
But doesn't it say that you can flow the identity bisections using precisely those vector fields rooted at the identity bisection locally to a vicinity of the identity bisection and thus getting enough bisections in the vicinity of the identity bisections, not necessarily sort of away from it. Isn't that?
Yeah, this is. I think you can read it like this, right?
Yeah.
Because sort of what comes next is sort of the following theorem. So we basically get a Lie functor which commutes with this bisection and the construction of the algebra of sections. So on one hand you have Lie groups. You have the Lie functor which spits out the associated Lie algebra. And if you go, okay, let's now fix the category of Lie groupoids over a fixed manifold M, basically because I don't want to discuss mappings which do not fix the base manifold because they are complicated to treat using these bisection things. So for every Lie groupoid over M, I can basically construct the bisection group. I can construct for this Lie groupoid its associated Lie algebroid, and basically you get a commutative diagram of functors, where when you take from the Lie algebra, you take minus the section algebra. I mean, the minus here just tells you that you need to take minus the Lie bracket the Lie algebroid provides to you. Then you end up with the Lie algebra of the bisection group. And
yeah. So in the sense, L could be trivial, yeah.
Sure. Yeah. I mean,
this bisection group could be trivial, say. So this the Lie algebra is 0, and this is just embedding of 0 in the Lie algebra. So this is only a functor, not isomorphic.
Yeah, but if it no, it's not isomorphic. No. I mean that's something you cannot get. Yeah. So I mean,
yeah,
this
because maybe I was wrong thinking that you speak about isomorphism.
No. This is, I'm not claiming that.
Probably you're right. Yeah.
Yes.
If the group, yeah.
This is exactly the question. So I mean, this was basically the question which back then when we were doing this work, Christoph and I were asking. So how much does the bisection group actually know about the underlying Lie groupoid? And do the bisection uniquely identify Lie groupoids? And the answer is no. Well, in general, there are too few bisections. This is exactly what we were discussing, right? So I cannot recover the Lie groupoid from the bisection group in general. But if I have the bisection group and a candidate for the action, so at least if there are enough bisections, and a sufficient topological condition was already named, namely that the Lie groupoid is source connected, then what you can prove is that if you build from this Lie group action here, the action groupoid, which as a manifold of arrows is basically just the Cartesian product of the bisections with M over M. So you're building this action groupoid, then the original groupoid is uniquely determined as a quotient of this action groupoid. So you can basically write down this action groupoid and a groupoid and recover G as a groupoid quotient when you're killing off here the what I want to say, the trivial bisections, so the ones which take values in the isotropy groups, which you don't see on
In
M.
fact, this is the definition of enough.
Yeah, if you exactly. Yeah.
So can you go back to the previous transformative? Yeah. So do I understand correctly? So the left arrow bis, this gives an isomorphism of groups. somehow. I mean,
Well, yeah, if you're, so what are the morphisms in this Lie groupoids over M? Those
Yeah.
are basically groupoid mappings, but which fix the space of objects. Yeah. So, and if you have an isomorphism there, then of course this just gives you an isomorphism here of the bisection groups.
no, okay, let me phrase it more as a question. So, what Janos said, so on the left-hand side, this map could be just going into 0 or something, or how is it? On the right-hand side, sorry. And on the left-hand side, probably you have a big group, but then on the right-hand side, you find in the Lie algebra sections, you find only a small part of the Lie algebra, or what? Do you misunderstand?
No, wait a second. Let's see. I mean, so how is it? I mean, okay. I mean, all of this, the L functor is basically giving you sort of an infinitesimal part, right? So and I mean, this is just, I mean, from all of the data of the Lie algebroid, you're just keeping the section algebra of the vector bundle together with the bracket. This is basically, I mean, the claim is basically that this is what the Lie algebra of the bisection group is, right?
But it's
At
apparently
least
small.
the Lie algebra of vector fields, which is the Lie algebra, the tangent bundle, completely determines the manifold. But in general, this is not true.
Yeah.
No, excuse.
Yeah.
I want to mention that we should think about the well-being of certain child waiting in a certain kindergarten, and for that I would like to remind you that it is 3:45 now.
Oh, yeah. So let me just finish with this. So basically, having enough bisections, I mean, this result is not it's just a reconstruction result in the sense that I already know what the groupoid is. There's this older paper together with Christoph where we're also looking into ways of cooking up. You give me an infinite dimensional group with an action on a finite dimensional manifold, and there's a way of cooking up a Lie groupoid for which the infinite dimensional group you start with, or I mean, it doesn't necessarily need to be an infinite dimensional group, but for which the group is the bisection group of the groupoid you've cooked up. So I don't think I have, yeah. So this is more in line of what a true reconstruction functor would be without pre-knowledge of what the Lie groupoid needs to be. And this is then, but this works only, I mean, I'm boldly writing these arrows here as something which is functorial, and this is true to a certain degree, but you have to be very careful what kind of data you need here. Actually, this is not really a functor on the category of Lie groupoids of Lie algebras. It would be very nice if you get a functorial picture here, but it's much more restricted. So this, take this with a large grain of salt, this picture. I just wanted to mention that there is something which you can do this. Okay, and then I'm hopping over. So here is actually the definition of a semilinear representation, but I will hop over these things. Let me just end with something of why we at least thought, I mean, what Christoph, the original co-author, who was in here, why we thought this is interesting, because at one point we hoped to understand better when an infinite dimensional Lie algebra can be integrated to a Lie group, because for Lie algebroids there is this nice integrability condition by this famous paper of Kreinich and Fernandez from the Annals of Mathematics, and they have a very explicit construction of the integrability obstruction to a Lie algebroid. And at some point we thought, okay, maybe we can use these bisection and reconstruction mechanisms to learn more about the integrability of Lie algebras. Also, we tried to apply it a little bit to the extension of infinite dimensional Lie groups, and the far-reaching goal at one point formulated was we can maybe look at low-dimensional homotopy groups of the diffeomorphism group. This never happened. I mean, I invite you to take a look at this paper here, reconstruction of Lie groupoids from their bisectional application to pre-quantization. This has several pages of open questions and problems we had, and I never revisited that. Yeah, so these problems are basically explaining things we at one point thought we would like to do, or we thought we could do using these kinds of techniques, but we never got around to this. And Christoph, the co-author, left academia several years ago. So yeah, unfortunately, I really don't have time to go into this. And I very much hate that I need to go, because there's lots of interesting discussions going on here. So, but for now, I must say thank you for the attention, and thanks actually for inviting me. I would be really happy to continue this discussion another day, because this is quite interesting. So yeah, okay, that's everything from my side.
Thank you very much. And I'm sure we can arrange something for the continuation of the discussion. And for now, you are free to take care of your children. Thank you.
All right.
All right.
Yeah. Thank you very much. And please, by all means, let's talk at another occasion. So send me an email in case you're interested. All right.
Yeah,
Thank you very
yes.
much.